Welcome back, everybody. Today, we're going to be talking about differentials, diamond operators, and the number field of a cusp form. So let's do that. So let's recall what a diamond operator is. It's a map that sends f to f bar k diamond of d, which is an endomorphism of s sub k of n. What is this diamond of d? For d and z mod n z cross, the diamond operator diamond of d is defined as f bar k of diamond of d is just f bar k gamma, where gamma in gamma 0 of n is any matrix which reduces mod n to a matrix with d as its lower right entry. Any such matrix will do. This is a well-defined endomorphism. We've talked about all this in previous videos. Recall, though, that you can also view these diamond operators as automorphisms of modular curves, hence as correspondences on these curves, because every automorphism of a modular curve is a correspondence. You can pick one map from the curve to itself to be the automorphism and the other map to be the identity. Okay. Now, using the theory from the last video, because the diamond automorphisms induce correspondences on modular curves, much like was done for the Hecke operators, one can create diamond of d operators on the space of holomorphic differentials omega 1 of x sub 1 of n slash c for all d and z mod n z cross. So just like Hecke operators t sub p can be thought of as operators on the space of holomorphic differentials for this complex modular curve, so can the diamond operators diamond of d for d and z mod n z cross. Okay, so proposition 16, remember from the last video, we have this canonical isomorphism of vector spaces S2n with omega 1 x sub 1 of n slash c. And remember that this commuted with that Hecke action. Okay, turns out it also commutes with the diamond action, diamond of d for all d and z mod n z cross. So what I mean by that is if you call this map psi like we did last time, psi of diamond of df is the same as diamond of d psi of f. Okay, where diamond of d on the left hand side is the diamond operator, and diamond of d on the right hand side is induced by the diamond correspondence, let's call it. Okay, so consequences of this canonical isomorphism and its equivariance with respect to the Hecke and diamond actions, it follows from these two propositions, the one I just covered and the one from last video, that S2n has a Q form that's stable under all the Hecke operators T sub p and all the diamond of d's for all d and z mod n z cross. And the reason for this is very simply because of the canonical isomorphism. Omega 1 x sub 1 of n slash c has that property because there's a model of this curve x sub 1 of n over q. Okay, that's what's going on here. So if S2n chi contains a Hecke eigenform for which TP has eigenvalue, let's call it lambda p, then for any sigma and aught c, so for any automorphism of c, S2 of n chi acted on by sigma, so sigma of chi, contains a Hecke eigenform for which TP has eigenvalue sigma of lambda sub p. So what's going on here is you've got a Hecke eigenform, let's say, in S2n chi. Let's call its eigenvalue lambda sub p. What I'm saying here is that if you act on chi with sigma, giving you chi to the sigma power, which is just really shorthand for sigma of chi, then this space S2n chi with sigma acting on it will contain another Hecke eigenform for which TP has eigenvalue not lambda p, but lambda p acted on by sigma. Now I should tell you what is the actual action on the space of Dirichlet characters mod n by aught c. So that's very simple. To act on chi by sigma, you just take x and you send it to sigma of chi of x. And it's the exact action you would think it is, in other words. Okay, now in fact, so we've seen that Fourier coefficients of a normalized Hecke eigenform are polynomials with integer coefficients in the Hecke eigenvalues and chi values. See the discussion just prior to proposition 10 in a previous video. Okay, so what this allows us to do, since we know all of this now, we can define an action of aught c on the set of normalized Hecke eigenforms in S2n as follows. Let's take f with its usual Fourier expansion with coefficients a of n, and let's send it to what we'll call f of sigma, or sigma acting on f. And that'll be the normalized Hecke eigenform whose Fourier coefficients are the a of n's acted on by sigma in the way that we just described. Okay, so you can send f to f acted on by sigma, and what you do is you essentially just act on the coefficients by sigma. That's all you do. Okay, so this is an action of normalized Hecke eigenforms in S2n. Okay, it turns out that if f is a new form of level n, then so is f acted on by sigma. And this is just a quick argument using theorem 6 from a previous video. Now, all of this to say, this whole last slide essentially is to say that the map that sends f to f acted on by sigma this just defines an action of odd C on prim2 of n, the space of primitive forms of weight 2 and level n. Now remember, prim2n is a finite set. So S2n new, we know is finite dimensional and has a basis of primitive forms. That was a proposition we had. Well, if it's a finite dimensional space, then all of its bases are finite. That's what's going on here. Okay, well, fine. So we have an action of odd C on a finite set, prim2n. So that means if F is in prim2n, the field, which we'll call KF, which is Q, adjoin all the Fourier coefficients of F, has finite degree over F because of this finiteness of this set. And so it's a number field. And so this is fantastic. You can also see Diamond and Sherman chapter 6. In fact, Diamond and Sherman chapter 6 is a great reference for this entire video. Also, DDT talks about this a little bit. But what we've just discovered, and there's more than one way of proving this. The way we've done is just one way. We've discovered that if you take a normalized Hecke eigenform, so a primitive form of weight 2, level n, and you take Q and you adjoin all of its coefficients, even though there are infinitely many coefficients, right? I mean, this is a whole Fourier series that this thing has. This is actually a number field over Q. It's a finite field extension of Q, okay? And so if you go all the way back to my first few videos, we talk about this and we use this fact a bunch to do various things with abelian varieties and so forth, okay? And so I'll end the video with this, a neat consequence, whose proof is fairly involved, so I won't go through it, but it's a consequence of everything we've talked about today. S2n has a basis of forms with rational integer coefficients, okay? This is proven in Diamond and Sherman chapter 6 and also DDT page 38, I believe, okay? And so next video, we will push further and we will begin to route our way back to modularity. So I'll see you then, and thanks for watching.